Hello, my name is Samuel Hui, and today we'll be going over part C and D of problem 3 of exam 4. So, in the problem, we are told that a satellite of mass m is attached to a rocket of mass curvy m, and it's being launched from the planet X, the mass and radius of which I've written here, at a velocity that's tangential to the planet, from point A. It follows an elliptical orbit so that it ends up being at point B, which is an altitude of 2r above the planet. It then explodes in a way that the rocket is held stationary, but then the satellite follows a circular orbit around the planet at an altitude of 2r. So then we are being asked to find what velocity is the system being launched at exactly in part C. Now, we can recognize that we can apply the law of conservation of angular momentum. Why? Well, we can only apply that when there's no net torque. Well, look at the forces that are being acting on this system. It's just gravity. Gravity is pointing towards the center of mass, so then the angle between that force and the angle between then the angle between the force and the distance from the axis of rotation, which is the center of the planet, will end up being 0. So no net torque. So then let me just write down the thing and about X's center. And what I mean by I and F. I is at A and F is at B. Now we know that angular momentum can be calculated by the mass of something times its linear velocity times its distance between that mass and the axis of rotation times sine of the angle between that distance and its linear velocity. At both points, it's still going to go at a its linear velocity is going to be tangential to whatever distance it is away from the mass. Just look, it's right angle because it's tangential, and we're being told that in the problem. Anyways, so then the initial linear momentum would be the combined masses of the rocket and the satellite times its initial linear velocity, which is what we're trying to find, times its distance that's away from the center of rotation, which is the planet's center, which would just be this planet's radius, and the final angular momentum, would be the same mass times the final velocity up here, times free r, because we're adding the altitude with the radius of the planet. And what we end up finding is that the final velocity is equal to vi over free. Like every system, we can apply the work energy theorem. And there's not going to be external work forces because the problem doesn't say that there are any. And it can be assumed that there is. That there isn't, based on how the problem is described. Now, kinetic energy of the thing would just be what it always is. Whatever the mass of the thing is, which is the combined masses, times 1/2 times initial velocity. And potential energy, we have to use gravitational potential energy, which would just be gravitational constant times the combined mass of the system times the mass of the planet, which I said before, times its radius, which at its starting point it's r, and final energy would just be more or less the same, except we have to change a few things. For example, final velocity is vf squared and the radius is free r. Things end up canceling, and what we get for a final answer is vi equals free gm over 2r. That's our answer for C. We can take this a step further and find that our final velocity is just that divided by 3, so gm over 6r. Part D asks us to find the ratio between the rocket's mass and the mass of the satellite. To find that, we can realize that the final mass after the explosion, that the final velocity that the satellite needs to be going at after the explosion needs to maintain centripetal motion at an altitude of 3r, a distance 3r from the center of its circular motion. If we call into the planet plus r and sum up the forces and realize that our only force that's acting against the system, the mass of the rocket, is gravitational force, which equates to so from formulas that we covered in class. We can equate that to the centripetal motion I was talking about, which is the centripetal force that I was talking about, which is this. Now we need to find what the new initial is before explosion is initial and F is after, which means that the VF from the last problem is now our VI. Anyways, we end up getting that the final velocity of the satellite should be gm over 3r and take the square root of that. Am I getting that right? Yes, I am. For the same reason that we could apply conservation of angular momentum in part C, we can do the same in part D about the same axis of rotation, which is the planet's center. And for the formula that I already talked about, the initial would just be this. And equate that to the final thing. Well, this is held stationary, so the rocket has no momentum, but the satellite does, and it's just its mass times that velocity we just found. Times 3r. That's a final. That's a total final angular momentum. Then you solve that out, and then you end up getting something like this in your problem. You can perfectly divide this out and get that. Get this as a ratio and our answer to D. Thank you for watching.